Welcome back to another video for IB Environmental Systems and Societies. Today we're going to go through the first part of topic 8.1, Human Population Dynamics. The big idea here is that we have a variety of models and indicators we use to quantify or measure the way that human populations change. The example on the screen are called age-sex pyramids. We'll do quite a bit of work evaluating and analyzing those. The model you see here on the screen is called the Demographic Transition Model, or DTM for short. If you're taking IB ESS, you may encounter this model in your geography class, or you may have had it previously in an individuals and societies class. What this shows is how different factors, such as birth and death rates, impact the way that human populations grow and change over time. The demographic tools that you need to be able to use for topic 8.1 are the crude birth rate, the crude death rate, the total fertility rate, the doubling time, and the natural increase rate. Very simply, the crude birth rate is simply the number of births per 1,000 people. Note, it's not per 1,000 women, it's per 1,000 people. In this graph, you can see a very clear trend here. Starting in the 1950s, there were approximately 37 births per 1,000 people. By the time we get to the current era, that level is closer to 17 births per 1,000 people. This is a falling crude birth rate, and we can infer several things about society from that information. We'll get to that later. The crude death rate, just like the crude birth rate, is a simple measure of the number of deaths per 1,000 people. On this graph, also showing the demographic transition model, you can see that in early stages of the transition, both the crude death rate and the crude birth rate are quite high. Initially then, the death rate starts to fall. That's usually the first sign of a change in socioeconomic development status of a nation. The birth rate remains high, typically because culturally people have become used to needing to have many children because many children frequently died. It's only after a sustained period of time in which fewer children are dying that the birth rate begins to decline as well. The fertility rate is the number of children an average woman has during her lifetime. I believe in Niger, it's currently around 7. The total fertility rate is a more nuanced statistic. It's the average number of children that would be born alive to a woman or a group of women during her lifetime if she were typical. So it's a statistical measure. The fertility rate is based on past data. The total fertility rate is based on past and future predictions. The total fertility rate, as you can see here, predominantly this big bright red and orange zone, Sub-Saharan Africa, Afghanistan, parts of the Middle East, significantly high fertility rates. The cool blue colors reflect low fertility rates, and those generally correlate with places where populations are either steady or beginning to decline. The doubling time, as you might guess by its name, is simply the number of years it takes for the population of a given country to double. It's related to the natural increase rate. The faster a population is growing, the shorter the doubling time. If a population is growing slowly, it takes longer for the population to double. So it's simply divide 70 by a number called the natural increase rate. The natural increase rate is simply the difference between the crude birth rate and the crude death rate. So if you have the CBR, the birth rate, and the CDR, the death rate, you can calculate the natural increase rate by simple subtraction. Then from that, you can calculate the doubling time by taking the number 70 and dividing it by that difference. Pretty straightforward. You may be asked to explain the relative values of the crude birth rate, crude death rate, total fertility rate, doubling time, and the natural increase rate. How do each of these impact the total population? As long as the birth rate and the death rate are relatively equal, you'll have times where the population is relatively stable. If the death rate, which you can see here in this green curve, if the death rate begins to exceed the birth rate, the population will decline. If the birth rate exceeds the death rate, the population will increase. So the difference between these two lines here is the natural increase rate. In early stages of the demographic transition model, you have high birth rates and high death rates. In the second stage of the demographic transition, we see falling death rates while birth rates remain high. In the third stage, birth rates begin to decline and approach those of the death rates. So the growth, the total growth or the natural increase rate of the population begins to slow down. In the fourth stage, which we see in well-developed, more economically developed countries, or MEDCs, we have relatively low birth rates and relatively low death rates. Therefore, we have stable populations. And where the human population may go into the future is still unknown. It's still unpredictable. But in some very highly developed nations, such as Japan, Sweden, Norway, Denmark, we're beginning to see death rates that exceed birth rates and shrinking populations. Probably one of the most common tools that you'll see when dealing with human populations are these age-sex pyramids. And you should be able to relate the shapes of these pyramids to the different stages here in the demographic transition model. So this stage one, where you have rapid growth, okay, you have a very high birth rate, which you can see by the very wide base. And because it has a narrow top, it narrows quite quickly. That also indicates that there's a fairly high crude death rate. In stage two, this slow growth, that correlates right here, where you still have a relatively high birth rate, but a declining death rate. So people are beginning to live longer, but the birth rates are still high. In stage three, right, where the birth rates begin to approach those of the death rates, we have a population that is stabilizing. And so here, as you can see, where you have these sides that are fairly straight or vertical, that indicates that more and more people are living to an older age. So the death rates are definitely declining. In stage four, here it's got the question mark. That's this section down here, actually, where the birth rates are now fewer or lower than they were previously. So here, there were a lot of births. And over here, because of the width of this area, it's lower births. This population is aging. There are fewer young people to replace the old people. I've got some worksheets available on my website if you want to check those out to help you work through this analysis. As usual, in ESS, you may be asked to discuss the effectiveness or use of models. These age-sex pyramids, the demographic transition models, they are models. They have strengths, they have weaknesses. That's the type of discussion and evaluation you may be asked to do on your ESS exam. That's it for today. I hope you found it helpful. I'll be back soon with the follow-up part of this video where we go through the rest of topic 8.1 and we look at the factors affecting those human populations. If you found this video helpful, please consider subscribing to my channel, give it a like, and help me grow the audience to reach more ESS students around the world. Happy learning. Welcome to another IB Environmental Systems and Societies video. Today's video is about ESS Topic 8.2, Resource Use in Society. This topic examines how humans use natural resources and the implications of that use for sustainability. As you can see from this crowded street scene behind me, our growing population creates increasing demands on Earth's resources. We're going to explore the concepts that are going to help you succeed in your ESS exams, so let's get into it. Renewability depends on how quickly resources can be replaced in nature. Renewable resources can be generated or replaced as fast as we use them. Replenishable resources are replaced more slowly, but they can be replaced. Non-renewable resources are finite and cannot be replaced within human timescales. Remember from topic 1.4 that sustainability means using resources at a rate that allows for natural replacement. Renewable natural capital includes resources that can be replaced quickly. This includes living species and entire ecosystems that harness solar energy through photosynthesis. Examples include forests, fish populations, and agricultural crops. It also includes non-living components like groundwater and the ozone layer. These renewable resources naturally restock themselves through growth and are often, but not always, the biotic components of ecosystems. Non-renewable natural capital can't be replaced within human timescales. These resources formed over geological time periods spanning millions of years. Fossil fuels like coal, oil, and natural gas are prime examples. Once they're burned, they can't be regenerated. Similarly, minerals and soil take extremely long periods to form. When we extract and use these resources, we're depleting a finite supply. Renewable natural capital can be used either sustainably or unsustainably. The key concept here is natural income, the growth or yield produced by natural capital. Examples include agricultural harvests, timber growth, or increases in animal populations. When harvest exceeds growth, we deplete the resource. A sustainable approach ensures that we only use the natural income and we preserve the original capital. Natural income is like interest from a bank account, except instead of increasing your money, you're growing natural resources. If you only spend the interest, your original savings remain intact. With natural resources, if growth exceeds the harvest, then stocks will increase. But if the harvest exceeds the growth, stocks will go down. Sustainable use means using only what regrows, like cutting trees at the same rate that they regenerate or catching fish at the same rate that they reproduce. Even renewable resources can become unsustainable due to how we extract, transport, and process them. Take fishing as an example. Technologies that increase fishing efficiency can lead to overharvesting, and that depletes fish populations faster than they can reproduce. This creates a destructive cycle. As fish become harder and harder to find, fishing technologies become more aggressive, and that further depletes populations until a collapse occurs. For your exams, you need to outline examples of mismanaged resources. Choose one renewable resource, like solar energy in Africa, and one non-renewable resource, like fossil fuels. For each of those, you should identify sustainable management strategies, contrast them with the actual practices, and then describe the consequences. Consider why resources with abundant potential, like solar energy in Africa, might not be optimally utilized. The second significant idea is that the status and value of natural capital is dynamic. It changes over time. Resources don't always have purely economic value. They may have cultural, religious, or intrinsic value. Remember the environmental value systems from topic 1.1? People with different EVSs will value resources differently, from ecocentric to technocentric perspectives. Natural capital provides both goods and services. Ecological goods are tangible products like metals from ores, electricity from water, crops from soil, and timber from forests. These are physical resources that we extract and use. However, many of the most important benefits from nature aren't physical products at all. Values of natural capital can be categorized as use values or non-use values. Use values require human interaction with the resource, like direct use of timber or indirect use through ecosystem services. Non-use values exist whether humans interact with the resource or not. It's like an existence value, right? That's valuing that something simply exists, or a bequest value, which is preserving resources for future generations. Ecological services are benefits that are provided by ecosystems which aren't typically monetized in traditional markets. These include oxygen production, carbon sequestration, water purification, flood control, and climate regulation. Without these services, human societies can't function, but we rarely pay directly for these services. This makes them vulnerable to degradation because their value isn't actually reflected in market prices. Mountains provide a bunch of different ecological services. They store water as snow and ice, they regulate climate, they protect watersheds, they provide habitats for unique species, and they offer spiritual value to many cultures. Some goods from mountains include minerals, water for hydropower, medicinal plants, and agricultural products. Understanding these interconnected benefits is what helps us recognize the full value of ecosystems. The value of natural capital varies dramatically over time. This graph shows uranium price fluctuations over many decades. These changes reflect shifting technological, political, and environmental factors. For example, prices peaked in the 1970s during nuclear power expansion, and then they fell after accidents like 3 Mile Island and Chernobyl all raised safety concerns. More recently, climate change concerns have renewed interest in nuclear energy, and so its price is climbing again. The dynamic nature of natural capital is perfectly illustrated by coltan, a mineral once considered nearly worthless. It contains tantalum, essential for manufacturing electronic capacitors in smartphones, computers, and gaming consoles. As technology has evolved, the demand for coltan skyrocketed. Now it's mined in conflict zones like the DRC, where its extraction funds armed groups and causes environmental devastation. Different cultures value natural resources differently. Consider wildlife reserves in East Africa. Tourists value them for viewing wildlife, while many local communities might value them for grazing livestock or hunting. Similarly, wilderness areas might contain plants with medicinal properties, and that creates ethical dilemmas. Should we protect pristine wilderness or explore it for potentially life-saving compounds? These kinds of questions highlight how resource management involves complex value judgments. That's it for topic 8.2, resource use in society. If you remember these tips when you're studying, you're going to do well in your ESS exams. Good luck, and until next time, happy learning. Welcome to another IB Environmental Systems and Societies video. Today's ESS topic is 8.3, solid domestic waste. In this video, we're going to explore how growing populations and consumption patterns are creating significant waste challenges around the world. We'll examine disposal options, management strategies, and the circular economy approach to sustainability. Let's get into it. Solid domestic waste is increasing due to growing human populations and rising consumption rates. That means more people are using more stuff. This creates serious environmental challenges as communities struggle to manage waste effectively. The amount we consume directly correlates to the waste we produce, and that makes this a really important issue for sustainable development. Looking at Hong Kong's data from 91 to 2017, solid domestic waste increased pretty significantly, peaking around 2004 before it started declining. The three most commonly recycled materials were paper, ferrous metals, and plastic. In 2010, ferrous metals made up about 20% of all recyclables that were recovered. This shows how recycling efforts can help manage increasing waste problems. Non-biodegradable waste, especially plastic, batteries, and e-waste, has become a huge environmental issue. Unlike organic waste, these materials persist in the environment for decades or centuries. E-waste contains valuable resources, but it's also really hazardous, and that makes proper disposal really important for environmental protection. The United States uses four main disposal options: landfilling, recycling, incineration, and composting. Each method has advantages and disadvantages based on environmental impact, cost, and resource recovery. Note that in some contexts, incineration is also called combustion with energy recovery. The waste management hierarchy shows us that prevention and reduction are the most preferred options, following by reuse, recycling, energy recovery, and finally, disposal, or throwing things away into a landfill. This pyramid represents the relative effectiveness of each approach. Composting falls under recycling, while reduction requires changing consumption behaviors and patterns. The significant idea here is that both production and management of solid waste influence sustainability. The circular economy model transforms our approach from a linear take, make, dispose model to a system where materials continuously cycle through production, consumption, and recovery phases. This shift reduces virgin material extraction and helps us conserve our resources for future use. Different strategies for managing solid domestic waste exist at three different levels, and you should recognize this from the three-tiered approach to pollution management that applies to any kind of pollution that you encounter in the ESS syllabus. The first tier is altering human activity. That's the most fundamental and the most effective. The second tier is controlling the release of that pollutant into the environment, such as through regulating standards. And the third and least effective strategy is generally cleanup and restoration. This is least preferred because it tends to be the least effective and the most expensive. Examples of different strategies include campaigns, education, legislation, economic incentives, and technology for extracting pollutants. And each one of those tiers addresses different stages of the pollution process. This detailed graphic shows pollution management across four phases: sourcing, production, use, and end of life. Each phase contains specific strategies. For example, sourcing strategies include renewable materials, while production focuses on efficient manufacturing. These connect to the three management tiers from the previous slide. Waste to energy facilities manage solid domestic waste by converting it to electricity through combustion or burning. The process includes pollution control systems to remove toxins, mercury, acid gases, and particulates from the exhaust. This helps address the cleanup and restoration tier while generating energy, but it still produces ash, and that ash does require landfill disposal. Disposal options for solid domestic waste shifted pretty dramatically since 1960, with recycling and incineration growing while landfilling decreased. This shift resulted from environmental awareness, from economic factors, and from changes in regulations. The waste hierarchy explains why certain options are preferred based on environmental impact and resource conservation. When we take a look at this EU data, we can see significant variation in waste management approaches. Northern European countries like Denmark and the Netherlands emphasize recycling and incineration, while southern countries like Greece and Ireland rely heavily on landfilling. These differences reflect economic, cultural, and policy variations between nations. And notice when we say Northern European countries and Southern European countries, we typically are referring to the economic status of those countries and not their geographical location. When evaluating solid domestic waste strategies, consider system inputs, outputs, and connections to other systems. Effectiveness relates to overall waste reduction, while efficiency considers reduction per unit cost. Strategies also vary in their effectiveness for different waste types and impacts on ecological, economic, and social systems. This comprehensive framework evaluates pollution management strategies from recycling to landfilling. Each option has specific application contexts, potential environmental impacts, challenges, advantages, and opportunities. For example, mechanical recycling works for specific plastics, while incineration handles diverse waste streams, but produces emissions requiring control. Pollution crosses borders, and that affects multiple countries. E-waste often ships from developed nations to developing nations, while marine litter like the Great Pacific Garbage Patch affects international waters. Development level influences solid domestic waste generation and management capacity, with high-income countries more capable of managing the streams than low-income countries, but also producing more waste than low-income countries. The circular economy represents a fundamental paradigm shift in how we view resources and waste. Instead of disposal, it emphasizes continuous material cycling, and that changes our fundamental economic model. This transformation affects not just waste management, but our entire perspective on resource use and environmental responsibility. That's it for ESS Topic 8.3 Solid Domestic Waste. On your exams, remember to discuss how growing populations and consumption create significant waste challenges around the world. Then, use the three-tiered approach to pollution management to explain and analyze different disposal options and management strategies for solid domestic waste. Until next time, happy learning. Welcome to another IB Environmental Systems and Societies video. Today we're going to review ESS Topic 8.4, Human Population Carrying Capacity. We'll explore how many people Earth can sustainably support, what ecological footprints are, and why it's so difficult to quantify human carrying capacity. So let's get into it. A key significant idea for this topic is that human carrying capacity is difficult to quantify. Unlike other species, humans have complex impacts on Earth. As the cartoon shows, we can't simply ignore connections between population growth and environmental issues. This difficulty in measuring carrying capacity presents major challenges for environmental planning. Carrying capacity is the maximum number of a species that can be sustainably supported by a given area. For most animals, this concept is pretty straightforward. There's a limit to how many deer or rabbits an ecosystem can support. But for people, it's much more complex because we modify our environment and we import resources from outside our immediate ecosystems. Estimating human carrying capacity is problematic for three main reasons. First, we import and export resources between ecosystems. Second, we substitute resources when some become scarce. And third, we develop new technologies that change how we consume and use resources. These factors make our relationship with Earth's carrying capacity unique among all species. The ecological footprint, or EF, offers a solution. It's a model that helps determine whether human populations are living within their carrying capacity. Rather than asking how many people an area can support, the EF asks how much area is needed to sustainably support a given population. This reverse approach makes human impact measurable. An ecological footprint measures the area of land and water required to support a human population at a specific standard of living. It includes land for carbon absorption from fossil fuels, forests for timber, cropland for food, grazing land for livestock, fishing grounds, and built up land. All these are measured in global hectares. The ecological footprint model helps estimate demands that humans place on the environment. It considers various activities like built environment, agriculture, fishing, forest use, grazing, and fossil fuel consumption. Remember, these activities vary pretty significantly between less economically developed countries and more economically developed countries. Generally speaking, the more economically developed a nation is, the higher its ecological footprint will be. Ecological footprints vary significantly by country and individual. Factors include lifestyle choices that are shaped by environmental value systems, productivity of food production systems, land use patterns, and industrial activities. If a population's ecological footprint exceeds the land area that's available to it, that population is living unsustainably and they are exceeding carrying capacity. Take a look at some global ecological footprints, and you can see some pretty dramatic differences between them. Countries with the biggest per-person footprints include Qatar, Kuwait, the UAE, Denmark, and the United States. African countries generally have much smaller footprints. These differences reflect consumption patterns, development levels, and lifestyle choices between LEDCs and MEDCs. Environmental degradation and consumption of finite resources will eventually limit human population growth. As shown in this image, pollution, resource depletion, and habitat destruction reduce Earth's capacity to support human populations. These kind of impacts create real limits to growth, even if they're hard to quantify precisely. If human populations don't live sustainably, they risk exceeding carrying capacity and collapsing. The graph shows how populations can overshoot carrying capacity, thus depleting natural capital and causing a population crash. That leads to a degraded carrying capacity, which makes it harder for future sustainability to be achieved. Rapid population growth creates challenges at multiple scales. Food supply, resource availability, environmental quality, and economic systems all face increasing pressure. Different sectors of society experience these impacts differently, and that affects international relations, and it creates both local and global consequences. This map shows ecological footprints by country, with darker colors indicating larger footprints. Notice how MEDCs generally have larger ecological footprints than LEDCs. This reflects differences in consumption patterns, industrial development, and lifestyle choices across different societies and economies. Environmental value systems also significantly impact ecological footprints. Different worldviews lead to different consumption patterns and environmental impacts. As the cartoon illustrates, short-term thinking about development can have long-term environmental consequences. Understanding these connections is really important for sustainable decision making. International mindedness connects to sustainability through global resource management. Resources don't respect national boundaries, and that makes cooperation super important. From a TOK perspective, measuring human carrying capacity involves both objective data and subjective interpretation. And this highlights how environmental science combines empirical evidence with value judgments. That's it for our review of ESS Topic 8.4, Human Carrying Capacity. Remember that an ecological footprint is a useful tool to assess sustainability and resource use. You should also explain how human behaviors that are different from other species are what make it hard to reliably calculate an ecological footprint for different societies. Good luck with your ESS exams, and until next time, happy learning.